Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your Sumam. My channel name is also Sumam. You can watch my videos on my channel. If you found useful, please don't forget to like, share, comment and subscribe. Your comments are highly valuable to me. Please don't forget to press the bell button to get the notification of next video. The topic for today's discussion is energy correction factor. It is indicated by the notation alpha. Before discussing about energy correction factor alpha, let me start the discussion from the definition of Bernoulli's equation, which states that for a steady irrotational flow of incompressible fluid, total energy at any point is constant. That is, the summation of velocity head and pressure head and position head that is equal to constant, and this constant is varied along a streamline. So this equation that is varied under certain assumptions. The first assumption is flow is steady, that is flow characteristics as well as fluid characteristics are constant with respect to time. Second one is flow is ideal, that means fluid possesses no viscosity, that means there is no frictional resistance or there is no loss. Third one is flow is incompressible, that means the density of the flowing fluid is constant. Fourth one is flow is one-dimensional, that means this equation is derived for the motion of the fluid element along the streamline. Fifth one is flow is continuous and velocity is uniform over the section. The topic energy correction factor alpha that arises based on the concept of uniform velocity over the section. So based on Bernoulli's equation, the total energy at any point is constant. Bernoulli's equation is obtained from the conservation of momentum for the fluid particle moving along a streamline. Based on Newton's second law of motion, Bernoulli's equation can be viewed as work done by pressure force and gravity force on the fluid particle that is equal to increasing kinetic energy of the fluid particle. So let us apply this Bernoulli's equation at 2 points in flowing fluid. So consider the flow through a pipe of constant cross section. The discharge Q that is flowing through this pipe segment. Since the cross section is same throughout, velocity is same at the section 1 and 2. Consider another pipe segment which has a reduction in area at the section 2. Due to the reduction in the cross section area, velocity at the section 2 that increases compared to the section 1. So if you are applying this Bernoulli's equation at these two sections, we can write P1 by rho g plus V1 square by 2g plus Z1, that is total energy at the section 1 that is equal to total energy at the section 2. But for real fluid, we have to consider the losses that taking place when the fluid moves from the section 1 to section 2. So for real fluid, this equation is modified as P1 by rho g plus V1 square by 2g plus Z1 that is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL, that is the head loss. Here this V1 and V2 that considers at the section 1 and the section 2, that is the average velocity that we can obtain by the equation V equal to Q by A. So the summation of pressure head and velocity head and position head that is equal to total head, or it is also called hydrodynamic head. So one of the assumptions that is used for the derivation of Bernoulli's equation is the concept of uniform velocity over the section. So if you are considering the flow through a pipe, then the velocity that is uniform throughout, or the velocity V that is equal to Q by A, that velocity is considered uniform across a section. But we have learned previously that velocity for a real fluid that is equal to 0 at the boundary. So the velocity of the fluid particle increases from the boundary to the maximum value at the center. So the velocity profile, if you are drawing, it will be like this, or it is varying across the section. So consider a fluid element of area dA. So kinetic energy for that fluid particle that is equal to m into v square by 2, where m is the mass of this fluid that is passing through dA, then v is the velocity that is normal to it. So kinetic energy that is equal to m into v square by 2. Suppose rho is the density of the fluid, then So mass of the fluid that is passing through this area dA per unit time, that is equal to rho into V into dA or rho into dQ, and kinetic energy that is equal to rho into V into dA into V square by 2. So mass into V square by 2. So this can be written as rho into dA into VQ by 2. So if you are taking the cross section, velocity of the fluid particle is changing from the boundary. All the fluid particles are having different velocities. That is, along any cross section, the velocity of the flow will be different at different points, and the total kinetic energy possessed by the flowing fluid at any section will be obtained by integrating the kinetic energy possessed by different fluid particles. So total kinetic energy, that is equal to integral of this term, that is equal to integral across the section rho into dA into VQ by 2, that is equal to integral of gamma by 2g into dA into V cube, where gamma is the specific weight of this flowing fluid. So gamma, that is equal to rho g, or rho is replaced here by gamma by g. But if you are calculating the kinetic energy based on the average velocity, that expression is mass into V square by 2. Rho into Q represents mass of the flowing fluid into V square by 2. Whereas Q, that is equal to discharge equal to A into V. If we replace Q by AV, then this expression equal to rho into AVQ by 2, or it is equal to gamma by 2g into AV cube. So which kinetic energy will be higher? Definitely the kinetic energy calculated by integrating the kinetic energy of the individual fluid particle is higher than the kinetic energy that is calculated based on average velocity. Or we can equate these two kinetic energy as by using the term alpha, that is the kinetic energy calculated by integrating the kinetic energy of the individual fluid particle, that is equal to alpha into the kinetic energy calculated based on the average velocity v, or alpha equal to integral of dA into V cube divided by AV cube. The value of alpha is different for laminar flow as well as turbulent flow. So what is laminar flow? In laminar flow, Reynolds number is very less, or it is less than 2000 for pipe flow. And another characteristic of laminar flow is the fluid is moving in layers. So each layer is having its own velocity, or across a section there is a huge velocity gradient, that is zero velocity at the boundary, and it is increasing to the maximum value at the center. Whereas in turbulent flow, Reynolds number is high, it is more than 4000. So in turbulent flow, the fluid particles are moving in random manner, and there is a momentum transfer is taking place between the adjacent layers. So there is a well distribution of velocity. The variation of velocity is very less across the section, or it is more or less close to the average velocity. So if we are considering the value of alpha for laminar flow and turbulent flow, for laminar flow the value of alpha is high, that is equal to 2, compared to the value of alpha for turbulent flow, that is 1.03 to 1.06. And what is the role of alpha in Bernoulli's equation? So if you are accounting this energy correction factor alpha, then the Bernoulli's equation can be written as P1 by rho g, that is pressure head, plus alpha 1 into V1 square by 2g plus Z1, that is equal to P2 by rho g plus alpha 2 into V2 square by 2g plus Z2 plus HL. That is total energy at the section 1 equal to total energy at the section 2 plus HL, where alpha 1, that is the energy correction factor for the section 1, and alpha 2, that is the energy correction factor at the section 2. But unless otherwise specified, we need not consider the value of alpha. So we can follow the equation, that is total energy at section 1 equal to the total energy at section 2 plus head loss. So for solving problems related to Bernoulli's equation, if the alpha value is given to you, then you have to account that value, or you have to use this equation. Otherwise we have to follow this equation. Now the session comes to an end. For the time being it is enough. Thank you. Please don't forget to Press the bell button to get the notification of next video.